Replic's coding assistant deleted an active production database, despite explicit system instructions forbidding it. OpenAI's operator bypassed user confirmation safeguards to execute unauthorized Instacart purchases. The New York City government launched a business assistance chatbot that actively distributed illegal advice. According to internal benchmark evaluations, the models driving each of these agents were deemed highly capable and cleared for production prior to deployment. Graphing model accuracy against release dates shows mean task success climbing steadily at 21% per year. But panning right, operational reliability over that exact same timeline is virtually flat, growing at just 3% per year. The industry standard for evaluating these systems relies almost entirely on mean task success rates, a metric formerly known as pass at K. This measures whether an agent can successfully complete a benchmark task at least once in a given number of attempts. A mean accuracy score treats a predictable model that fails on a well-defined subset of tasks exactly the same as one failing entirely at random. It obscures tail risks and ignores whether the system can actually maintain its state under friction. To engineer systems that can operate autonomously, we must look to safety-critical engineering disciplines, translating their physical testing frameworks into computable machine learning metrics. Scaling parameters to increase raw intelligence does not organically solve for operational stability. If we evaluate capability without isolating reliability, costly production failures are a mathematical certainty. Certification for a commercial jet turbine demands precise, deterministic output under prolonged stress, treating reliability as a metric distinct from peak thrust. In aviation and nuclear power, reliability is an empirically measurable property. Certification in these fields requires quantifying exact failure probabilities and establishing strict degradation thresholds long before a system goes online. Applying this lens to AI agents gives us our first distinct metric: consistency. This measures whether a system produces the exact same outcome when executing identical tasks under identical conditions. Large language models introduce a specific engineering challenge: inherent stochasticity. Even with a generation temperature set strictly to 0, execution remains variable due to floating-point non-associativity and concurrent server batching. To measure true determinism, we shift from pass at K to pass and K, demanding the agent succeed across all 5 out of 5 attempts. This chart plots outcome consistency across 14 models. The data reveals a low ceiling. Even the most advanced frontier models fail to execute their successful tasks consistently across repeated trials. To isolate the failure mechanism, we measure trajectory consistency, tracking the exact logical steps the agent takes during multi-step reasoning tasks. The results expose a clear pattern. Agents possess high distributional consistency, meaning they reliably select the correct action types. However, they lack sequence consistency. They execute those exact same tools in chaotic, unpredictable orders every time the task is run. An agent that cannot maintain a stable, repeatable execution sequence cannot be meaningfully audited for compliance. That internal variance makes an otherwise capable model an immediate liability in production. This brings us to the second pillar: robustness. This isolates the system's ability to degrade gracefully when its operational environment deviates from the nominal conditions it was trained on. We decompose this into 2 vectors. Fault robustness measures resilience against infrastructure disruptions like API timeouts. Prompt robustness measures resilience to semantic variations in how a user issues an instruction. Evaluating state-of-the-art models across both vectors reveals a deep asymmetry in where their vulnerabilities lie. Current models actually handle technical infrastructure faults reasonably well. When a web search tool returns an error code, agents generally maintain state, process the fault, and retry the action rather than abandoning the task. This graph plots prompt robustness. When we inject minor, semantically equivalent paraphrasing into user prompts, performance fractures. Models that navigate complex technical timeouts effortlessly fail entirely when a basic instruction is rephrased. Deployed agents operate in environments that shift continuously. Data schemas evolve, third-party APIs update, and phrasing varies infinitely across a user base. Testing agents against static, frozen benchmarks creates a false sense of security. Real robustness requires evaluating systems against parameterized, generative environments that actively simulate systemic friction. The third pillar is predictability, an agent's capacity to recognize what it doesn't know. Predictability is quantified using two submetrics, calibration and discrimination. Both are mandatory for safe human-in-the-loop systems. Calibration calculates the alignment between an agent's self-reported confidence and its empirical success rate. If an agent states it is 80% confident, it should succeed precisely 80% of the time. The data shows a clear positive trend here. Recent model generations have corrected the overconfidence seen in earlier iterations, aligning their stated confidence tightly with their actual capabilities. The critical failure point lies in discrimination. Measured via AUROC, this tests whether an agent's confidence scores actually separate its successful outputs from its incorrect ones. This chart focuses on discrimination performance on the complex Gaia reasoning benchmark. Despite achieving better calibration, the discrimination trend lines for the newest models are either plateauing or moving downward. If a model cannot reliably distinguish its correct answers from its hallucinations, system architects cannot program accurate confidence thresholds. Without those thresholds, the system cannot safely defer edge cases to a human operator. The final pillar is safety. In an operational context, safety strictly measures the system's ability to bound the severity of consequences when failures occur. A missing JSON bracket is a benign failure. Executing an unauthorized financial transfer or dropping an active database table represents severe harm. Standard accuracy metrics treat both of these outcomes as a single, identical failure. Safety must be calculated as an independent hard constraint. Using the classical Kaplan and Gehrig formulation, operational risk is the product of a violation's probability and the expected severity of that violation. This exposes the reality of tail risks. A system that behaves safely 99% of the time, but inflicts catastrophic, irreversible harm in the remaining 1%, is undeployable. This bar chart displays safety data from the TauBench customer service simulation, breaking down specific compliance violations across models executing long-horizon tasks. While newer models have successfully suppressed their overall violation rates, specific high-severity failures continue to bypass their internal safeguards. Financial accuracy errors, such as issuing an incorrect refund or processing an unauthorized charge, remain the dominant failure mode across every single model family tested. Agents are designed to trigger actions in external systems. Mitigating these high-severity tail risks is an absolute prerequisite, independent of how well the model performs on generalized reasoning tasks. Across these benchmarks, we see a structural reality. Scaling model parameters predictably improves baseline safety and calibration, but it completely fails to organically improve consistency. Larger models possess significantly more reasoning pathways to solve any given problem. That expanded capability actively increases run-to-run variance, degrading the stability of execution sequences. This forces engineering teams to explicitly delineate between deploying AI agents for augmentation versus pure automation. In an augmentation workflow, like an AI coding assistant, a human acts as the reliability backstop. The human reviews the code before it commits, safely absorbing the agent's variance. In an automation workflow, the agent's output is the final action. There is no human buffer. Inconsistent logic translates directly into unrecoverable system failures. Engineering teams must restructure how they define production readiness. The reliance on single-shot accuracy scores must be replaced with dynamic frameworks that continuously probe consistency, robustness, predictability, and safety under parameterized stress. Architectures engineered specifically to constrain variance and guarantee predictable execution will define the next era